Hello, welcome back to Piers Rocks. Today, updates on One ROM, the most flexible replacement ROM for your retro systems. It feels like I've been doing a whole bunch of work on One ROM recently in lots of different areas, and I haven't actually been talking about it much on the channel. So this video is going to fix that. I'm going to cover quite a few different areas that I've been working on. The first thing that I'm going to talk about are the available models that I'm heading towards with One ROM. Second, I'm going to talk about the new Limp Mode that I've added into the firmware. Thirdly, I'm going to talk about the 28-pin prototype that I gave a sneak peek of in a recent video. And then the final area, which will be covered in much more depth in a future video, is the area of management tools, where I've done a whole bunch of work on different management solutions for One ROM to analyse an existing One ROM, creating firmware for a One ROM and flashing it really easily. First though, I want to talk a bit about the RP2350 version of One ROM. And these are the 5 prototypes of the USB One ROM RP2350 version that I laid out in a very long recent video. And then in the last video, I talked about 5 reasons why the STM32 microcontroller is a better fit for One ROM than the RP2350. Now don't get me wrong, there's also reasons why the RP2350 is a better microcontroller for this solution than the STM32. But that video was really focusing on how the STM32 had some advantage over the RP2350. One of the reasons I gave was that I've had a whole bunch of assembly failures with the RP2350. And true enough, when these 5 boards came back from JLC recently, I had a quick look at them with my reading glasses and I can immediately spot something was off with one of the microcontrollers. And I wonder if you can see from this shot which one it is. I can see it looking at the image in OBS. We'll get a good RP2350 board and the bad RP2350 board under the microscope so you can see what I'm talking about. So what we're looking at here is one of the good RP2350 boards under my microscope. I'm recording this audio later in editing because I don't have a good audio capture solution at my microscope, and I'll apologise in advance if sometimes the image gets a little bit smeary. I don't have a super expensive camera on the microscope and it's quite hard to get focus and enough light on the solder and the pins involved. For reference, this is a 60 pin package, so there's 15 pins on each side of the RP2350. The pitch, so the distance between the centres of each of the pins, is 0.4 of a millimetre, so that's just about 18 milli-inches, thereabouts, 18 thousandths of an inch. And the actual pad sizes themselves are 0.13 millimetre, which are about 5 thousandths of an inch. The pads on the PCB are slightly wider than that. As I've said many times, I'm using the stock Raspberry Pi footprint for this part. The pins on the RP2350 are actually pads that start underneath the board and come up outside the sides. So what you're looking at here is the solder attached to the PCB pads, which comes out further than the chip, wicking up and attaching to the side of the pad on the side of the RP2350. And this is what you expect to see with a well-soldered RP2350. I'll just run the video from here and you can have a look around the chip. So as you can see, as I move around the chip, you can see that both on the bottom, the left-hand side, the top and the right-hand side, there's good fillets wicking up from the pads on the PCB to the pads on the side of the chip. Here we have the badly soldered RP2350, and if you've got a keen eye, you can already notice at the top and the bottom of the RP2350 something's wrong. The pins that are slightly shinier actually aren't properly soldered. Those are the tinned pads that we're seeing the light reflected off. And if I then tilt the PCB up, and again, sorry, it's a little bit blurry here, you can probably see that these do not look even. Some of the solder pieces are actually wicked all the way up to nearly halfway up the chip. That's a well soldered pin. Some of them aren't wicked up at all. In fact, in a few of the pads you can see a little bit of copper exposed where no copper has touched them, and then on the top here you can see a couple of pads distinctly are not touching. The PCB and the chip are just not soldered together at all. Now on the left hand side and the right hand side of this package are absolutely fine. All the pins are properly soldered. It's the pins at the top and the bottom of the PCB that are improperly soldered. And this has led me to speculate that what's actually happening here is that it's during the soldering process where I think a stencil is being used, placed on the bare PCB, and solder is being sort of smeared through the stencil onto the PCB. It's probably being smeared in one direction, either across from left to right or across from top to bottom, or, you know, the opposite way round. And some of these cutouts in the stencil, because they're so small, because the pads on the chip and the pads on the PCB are so small, solder is sometimes not quite going in, maybe due to the granularity of the solder paste that's being used here. And also I'm speculating if it's better when you rotate the RP2350 by 45 degrees. And in that case, because of the smearing action always being done at 45 degrees to any pad, whichever pad it is, some solder is always making it in, and therefore if you have your chip rotated at 45 degrees, you get better results. Look, I'm speculating here, and I don't think it should be the case that you have to rotate your chip at 45 degrees to get a good solder job. But this is the reality of getting boards fabricated, at least with JLC, using their basic assembly service. I've seen this on every single batch that I've had produced. There's been at least one failure to solder, and it's looked pretty much like this. Next, we'll talk about plans for One ROM models. And up until now, I've had both STM32 and RP2350 flavors of One ROMs, and I'm still going to continue that. But I'm renaming the STM32 models ICE, because the STM logo is blue, and I've renamed RP2350 Fire because the Raspberry Pi logo is kind of red. Also, ICE is intended to signify resilience and robustness and strength, and if I were looking for a One ROM to just go in a retro system and just happily plug away for the next 40 years, I'd be choosing the ICE version right now. Whereas the Fire version has more power, it has dual core, it has the PIOs, so it has the ability to implement much more advanced features on. So if you're looking for doing something quite advanced and funky with a One ROM, then the Fire version may be more suitable. And in keeping with these new models, I'm getting the ICE boards fabbed in blue PCBs, and the Fire ones fabbed in red PCBs. In terms of programming options, I'm planning to have USB and also serial wire debug, which I'm renaming the Pro version. USB is the easiest version to program. You just need a USB cable jacked into your One ROM, and at the other end you need a PC, a tablet or a mobile phone to program your One ROM. Pro requires an external debug probe between your PC and the One ROM. It only costs a few bucks, but it's an extra bit of kit that you need. But it gives you far more advanced programming and control of One ROM. For example, you can dynamically reflash One ROM while it's running using the Pro version. In terms of the matrix of combinations, I'm planning to have ICE and Fire and USB and Pro versions of each. Now you can build the ICE version with multiple different STM32 microcontrollers that have different flash capability and different maximum clock speeds. For the 24-pin One ROM, I'm planning to stick with the F411RE microcontroller for most of my boards. Maximum clock speed of 100 megahertz. It's more than enough for a 1 megahertz retro system like a Commodore 64, and it has a decent amount of storage, 512 kilobytes, which gives you plenty of room for lots of different ROM images. But there are more powerful versions available and versions with more storage. And then, as you may have picked up, I've been working on 28-pin version of One ROM, which should allow me to scale up to 64 kilobyte ROMs. In that version, I'm hoping to be able to combine USB and Pro onto the same circuit board, both have a USB jack and also the serial wire debug pins, so it combines both of those capabilities. And again, I'm planning to have ICE and Fire. You can see from the asterisks on the screen which models are under development and not yet available. You've seen me dangle in front of you the USB version of Fire, which I'm not going to do any more work on in this video. That'll be a future video, hopefully getting that prototype working. You will see in this video a bit more about the 28-pin version of ICE. Let's see that now. I've put on the screen here the pinouts for the 23-128 and 27-128 ROMs. The 23 series ROMs were mass programmable at factory. The 27-128 were EPROMs, erasable programmable ROMs. Both were used in retro systems. Some retro systems used the 23, some used the 27, some used both, but they're both 16 kilobyte ROM chips. When I produced my 28-pin prototype, I looked at the pinout of the 27128, not the 23128. So how do they differ? Well, the first difference actually is not relevant. The pin 1 of the 27128 takes a programming voltage when you actually program it using a traditional EEPROM programmer, which isn't relevant for One ROM. That's not connected on the 23128. Essentially, I can ignore that pin within One ROM. Pin 27 on the 27128 is a programming pin, which is pulled in a particular direction when programming the chip. On the 23128, it's a third chip select line. So that's the first key difference. On the 23128, there are 3 chip select lines on a 16 kilobyte ROM. On the 27128, there are 2, and in fact, they're chip enable and output enable. And that's the second difference, which is an important difference. On the 27128, chip enable and output enable are both active low. Essentially, they both need to be pulled low for the 27128 to provide data on its data pins. On the 23128, we have mask programmable chip select lines instead. So those can operate either as active low or active high, depending on how they were mask programmed at factory. And the same goes for the third chip select line. So at this point, you may see where this is going. I did realize that the chip select lines were programmable on the 23128. However, I didn't realize that there was a third chip select line I'd have to support on some systems. So here's the schematic of the 28-pin ICE prototype that I actually had manufactured several months ago, and I've only just got around to testing it recently. You notice on this schematic that I have the 14 address lines, so there are 14 address lines required for a 16 kilobyte ROM, and the output enable and the chip enable, CS1 and CS2 on the 23 series ROM, all connected to port C, the 16-bit GPIO bank on the microcontroller. This was to allow me to use exactly the same ROM serving algorithm, which is you read the entire 16-bit GPIO combining the address pins and the CS pins, do a CS test on just those lines, and then use the entire 16-bit GPIO as an index into a ROM lookup table. You can immediately see if I've got 3 CS lines, this approach isn't going to work, partly because I'm not looking it up as part of the 16-bit bank, and secondly because it won't fit as part of the 16-bit bank. I've got 14 address lines, I've got 3 chip select lines, that's 17 pins. On the STM32, which is used on the ICE board, that simply isn't going to fit. So I consider this a design flaw with this prototype, because I absolutely also expect to be able to support 32 kilobyte and 64 kilobyte, that's 256, 512 kilobit ROMs in both the 23 series and the 27 series ROMs. This approach simply isn't going to work for that. I did anticipate those larger ROMs, and I did put those additional address lines on the microcontroller, but on a different port. But I think I've got the mapping here wrong. I think what I'm going to have to do with my next version of the 28-pin One ROM is put all of the address lines on a single 16-bit port C almost certainly, because that's where the vast majority of the address lines are today, and put all of the chip select lines, whether they be programmable or CE, OE lines that are active low, on a different port. That's going to require me to change the ROM serving algorithm, and I'm going to have to do both a read of port B to get the chip select status, and also port C to get the address lines. Do the test on the chip select lines read from port B, and do the lookup based on the address index loaded in from port C. That might have the effect of slowing down One ROM's byte serving algorithms. Actually, I'm not sure it's going to. I may be able to get away with a 1 cycle penalty, so at 100 megahertz, that's 10 nanoseconds, or maybe even a 0 cycle penalty. Essentially, when you're writing ARM assembly, you pay a penalty if you load a value from memory or a hardware register and then immediately use it in the next instruction. The way the pipeline works on the ARM Cortex-M chips, it essentially is it's a 3-stage pipeline. So it's loading an instruction, it's doing some pre-stuff on the instruction, then it's executing an instruction. That's the way I think about it. It's probably not technically correct. That means that if the processor doesn't actually have the value that it needs to operate on at the second stage of the pipeline, it's going to stall for 1 cycle. When you get to the third stage of the pipeline and it's supposed to execute, you essentially lose a cycle. You can get around the penalty of that by interleaving instructions. So I think what I can do is load the port B with the chip select line status, then immediately load port C with the address line status, and only then test the chip select lines, see if we've got an active, and also only then load the byte from RAM using the address lines. Because I've interleaved those instructions, I don't end up paying any load use penalty, which I am paying in some circumstances in the existing byte serving algorithm. So as I say, I might get away with 1 cycle penalty or 0 cycle penalty for this approach. We'll see. But this means, I think, that I should be able to support 16 kilobyte, 32 kilobyte, and 64 kilobyte ROMs with the next version of 28-pin One ROM. Now, in terms of the firmware changes required to One ROM to support this 28-pin version, the 16 kilobyte ROM, which is what I've tested it with so far, the ROM byte serving algorithm basically needed no changes at all for this particular schematic because it's taken an approach so similar to the existing ROMs. I did have to make a bunch of changes to the supporting tooling to actually be able to encode a 16 kilobyte ROM image instead of an 8 kilobyte, 4 kilobyte, or 2 kilobyte ROM image. So it probably took me a couple of hours all told to implement the changes to get the 16 kilobyte version supported. And I'll show you now the video clip of me actually testing it out in my C64C, which has a 16 kilobyte combined kernel and basic ROM for the very first time. And sadly, I forgot to turn my microphone on. Now a quick look at the management options for One ROMs. This is where I've spent a whole bunch of my time over the last few weeks, where I want to make it really easy for people to get a new One ROM and program it, or to modify the One ROMs that they already have. And I have two solutions. I have a web version, which works just in the browser and supports One ROM USB. And I also have a desktop version, which is portable and works on Windows, Mac, and Linux, and supports both the USB and the Pro versions. What you're looking at now is the web version. This runs in Chromium-based browsers. So again, it's PC, Mac, and Linux. Also supports Android tablets and Android mobile phones. So with One ROM Web, you open it in your browser. You take your USB One ROM and you plug it into your PC or your Mac or your Linux box or your Android tablet or mobile phone. There we go, it's connected. Click connect on the web tool. Just out of shot here, I have to select the device that I want to connect to. That's a security feature of browser-based USB access. And I connect to it. And you can see it's read my One ROM. And it tells me what ROMs I have on it. And I happen to know that these are C64 set of ROMs. Let's say I want something different on my One ROM. I come down here and I select the hardware variant information from above. I select the latest firmware version. Let's put a VIC-20 set of ROMs on this. Tells me what it's going to program here. I'll click program, and now it's erasing one ROM, and it's reprogramming one ROM, and then when it's finished, it's going to reread the device information and show it to us up here. So now it's showing us that the VIC-20 set of ROMs is installed. It's that quick and easy to use One ROM USB with the web programmer. Now let's look at One ROM Studio, which is the latest programming tool for One ROM. And this is a native desktop application for PC, for Mac, both Intel and Apple Silicon, and Linux. And I've got it building for x86 and also ARM, so you can run this on the Raspberry Pi. This supports both USB models and Pro models of One ROM, so a single tool does it all. First of all, I'll demonstrate programming the USB device with this tool. So this is the same One ROM that I just programmed VIC-20 ROMs onto. I'll plug it in, and then I'll hit rescan. So it's detected there's a One ROM ICE connected. So let's scan that device. And that quickly, it's read the first 64 kilobytes of the firmware and figured out what's on this device, what firmware it's running, what model it's programmed for, and so on. And if I scroll down here, I can see the various details of the VIC-20 ROMs that were programmed onto it. So let's say I want to change this to be a 1541 One ROM. I go over to the Create tab. It's pre-populated the information about the board based on what it read. It's pre-selected the latest version of firmware that's available, and this is all pulling the latest versions from online. I select the 1541. I'm going to hit Build Image. Now, there's no ROMs included in One ROM Studio. The 1541 configuration is located on a One ROM server, and that points off to where the tool can find the 1541 ROMs. So when I hit Build Image, it will pull down the ROMs and actually create a custom firmware image for One ROM on the fly. So that's done now, and we can see down here the details of the ROMs that have been packaged up into this firmware. I can either save this firmware off and use the image to program in other tools, and I can reload that image into here if I want to, or I can flash this firmware to One ROM, which I'll do now. So this is busy off erasing One ROM and reprogramming it, and it will let us know when it's done. There we go, that's done. And then if I go back to the Analyze tab and redetect the device and then scroll down, I can see the 1541 ROM images are on here now. So that's the USB version. Let's take a look at the Pro version now. And I'm going to plug in my Raspberry Pi debug probe. It's plugged in, and rescan. And that's been detected as a CM/SYS DAP probe, which is just a generic debug probe. And I have a One ROM connected to this already. So I'm going to detect what this One ROM actually is by hitting Detect Device. So that's now read the One ROM Pro via serial wire debug, and you can see this has got an older version of firmware on it, 052. Surprisingly, it's also got the 1541 images on it. Again, I can go to Create and I can select a different set of ROMs. Let's use the 2040 disk drive DOS1 ROMs. Build that image. It's built. Let's flash it via serial wire debug to the Pro One ROM. That's flashing right now. I can see it's finished on the probe. It's finished on the application. And then I will reanalyze the device. It's updated to 5.3 firmware because that's what I just put on it. And I scroll down here and I have these are actually 2040 images despite the fact they're in a 4040 directory on Zimmers. So there you go. That's a very quick tour around One ROM Web and One ROM Studio. In a future video, I'll talk much more about what you can do with these tools and also how I went about building them. The vast majority of the code here is written in Rust and it's portable code. Even in One ROM Web, most of the code that's running behind the scenes to decode ROMs and so on is actually portable Rust libraries that I've built as WebAssembly code and is running natively within the browser. Limp Mode on One ROM. One day I flashed the firmware for a faster microcontroller onto a slower microcontroller, One ROM, and it wouldn't boot, and it took me ages to figure out why. So I introduced Limp Mode. The One ROM now detects if it's been flashed with an incompatible firmware version for its hardware and refuses to run that firmware and just sits there flashing its status LED so you know something's wrong. And it also allows the device to drop into USB programming mode so you can reprogram it, as opposed to the previous behavior, which it would try and run at the faster clock speed and lock up. I've also used Limp Mode for when you build a firmware with no ROMs in it. It flashes with a different sequence so that you know that you've got an empty One ROM. It's running just fine, it's just got no One ROMs to serve, so it can't serve them. And why would it be interesting to have a One ROM with no ROMs in it in the first place? Well, the main reason is for manufacturing reasons, right? If you want to sell One ROMs and you want to ship them without ROM images on them so you don't have to deal with intellectual property and copyright concerns, then I needed to support the ability to have 0 ROMs installed. So I'm actually expecting that this Limp Mode will get used. People will sell One ROMs and they'll ship them with no ROMs on them, and it will have a particular unique flash code so that you know it's got no ROMs when it arrives and you can program it. The reason it needs firmware flashed on it in the first place when it's shipped is so that it supports the USB programming mode that's required to use both One ROM Web and One ROM Studio. I hope you enjoyed this video giving you an update on what's going on in One ROM land. I hope it's got you all excited about what's coming up in the future. If you did find this video interesting and useful, please do stick around for the next video. I'm planning on getting RP2350's own back on the STM32F4 at some point by explaining 5 reasons why the Raspberry Pi is better than the STM32 microcontroller for this application. I'm also planning to do a deep dive into the management tools and the technology that goes into those. We'll be seeing me trying to get the USB version of One ROM Fire working, and I've got a new 28-pin design to produce. So, until the next video, rock on.